First of all, to form a hologram, a laser light source is required. This is directed at a lensless camera upon which the hologram will be recorded. The narrow beam must be expanded using lenses up to the camera dimensions, and to capture fast-moving objects, the laser should be pulsed. Pulsing the laser at the same frame rate as the camera allows recording of a holographic video, or holovideo. As objects pass through the beam, holograms of the objects are recorded at the sensor and stored on the computer for later analysis. A typical hologram from sea trials capturing a number of particles is shown here. It is possible to process each hologram in slices at increasing distances from the camera, identifying the three-dimensional locations of all particles captured in the hologram. In this example, we set our software to reconstruct from 100mm to 300mm in 1mm intervals. The software begins to generate slices as it works through the volume specified. Each slice is a full reconstruction of the particle shadows at that distance from the camera, and the scale of the particles is defined by the camera pixel pitch. With modern cameras, the pixel pitch allows for particles as small as 25 microns to be detected. It can be seen that particles will come into focus and then move back out of focus as the scan progresses. For automation, the software must perform the focus detection to ascertain the peak focus of each particle as it arrives. This hologram contains 4 such particles. However, we'll terminate this example here. The University of Aberdeen has a history of developing holographic cameras, with the latest being eHolocam, completed in the early 2000s. This camera consists of 2 separate housings. The large housing on the right contains the laser and control electronics, while the small housing contains the camera. The green overlay indicates the beam path between these. On the left, the camera can be seen within the Marine Scotland Aries sampling platform, the dark cylinder at the bottom just surfacing now. The right gives some indication of the scale of the Aries platform, which requires towed by crane. eHolocam is approximately 1 metre long by 30 cm diameter, weighs 90 kg and requires an external battery. We intend now to develop a much smaller system incorporating an internal battery, enabling simpler deployment. The proposed system will make use of modern sensor technology, offering much higher frame rates than its predecessor. The optical components will be mounted on an internal frame, expanding the beam within the main housing. The power supply components will be highly integrated to fit within the housing, and we will utilise a miniature embedded PC platform running Linux for the control system. Power will be supplied internally with a lithium-ion battery, and the housing will be rated for 150 metre underwater deployment. A single subsea connector will be used to charge the system and to configure it prior to deployment through an Ethernet interface. We intend also to further develop our field programmable gate array technology to accelerate hologram processing. FPGAs offer a higher throughput than standard processors, as they can be configured to highly parallelize processing. A standard computer scans a hologram in about 10 minutes. With our current FPGA design, we've reduced this to 2 minutes. We are confident that we can achieve a 10-second scan with further development in this area.